Alright, today we're going to do a few more examples on solving trigonometric equations using everything available to us. And remember, if you see another way to solve an equation, great. Several of these equations have multiple ways that are right in that they will get you to a solution. Of course, there are many more approaches that will take you further away from a solution. Not to say they're wrong, right? You can do the right thing and just get further away from your goal. So once again, what we need to do before we do anything else when it comes to solving these equations, and also verifying identities for that matter, is figure out a strategy. Figure out what we want to do, and then do it. So we've looked at a few already. We'll look at a few more in this video. One of which is cosine 4 theta plus cosine 2 theta plus cosine theta is equal to 0. And we want to find all solutions to that thing right there. And yes, it is feasible, I think, to do the double angle formula for cosine 2 theta to get it to maybe 2 cosine squared theta minus 1. Do a similar thing for cosine 4 theta, first to break everything down into cosine of 2 thetas, and then do the double angle again to break everything into 4 thetas, and that would give you a fourth order pseudo-polynomial. A polynomialoid, right? You'll have cosine to the 4th power of theta, and something something cosine squared of theta, and something something cosine theta, and something something constant, all equal to 0. You would then have to do some rational function analysis. You have to do a little synthetic division, but you could crack that equation up there using double angle formula, I think. I wouldn't do it, but it could be done, I want to say. Another, maybe more sane approach would be, wait a minute, we have all these formulas beyond just double angle. What if I did the sum to product identity for these first two terms here? And I'm thinking that because if I average those two arguments, 4 theta and 2 theta, that becomes 3 theta. But the difference, 4 theta minus 2 theta all over 2, that's just theta. That just becomes cosine theta. So if I do that, I get 2 cosine 3 theta cosine theta plus cosine theta equal to 0. So doing this approach, we actually get very quickly, very efficiently, a factored equation. And this equation here is true clearly when cosine theta equals 0, which happens at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on, pi over 2 plus k pi. And it's also true whenever 2 cosine 3 theta plus 1 is equal to 0, which means cosine 3 theta has to equal negative a half, which means if negative a half is cosine 3 theta, that makes 3 theta either 2 pi over 3 or 4 pi over 3. So your general solution then for 3 theta is 2 pi over 3 plus 2k pi, or 4 pi over 3 plus 2k pi. But again, that was for 3 theta. So to get at theta, we just take those equations, divide through by 3, and that gives us now theta is 2 pi over 9 plus 2k pi over 3, or 4 pi over 9 plus 2k pi over 3. And so you could, if you choose, take our 3 subsets, right, pi over 2 plus k pi, so that'd be 90 degrees and 270 degrees. You could convert 4 pi over 9 into degrees, and 2k pi over 3 into degrees, and just add a whole bunch, and add a whole bunch to the 2 pi over 9s. And you could, instead of using this k notation, which I'm hoping I'm selling you on, but if you don't want to do that, you still don't have to. You could write everything coterminal with blah, all those angles. And that would still be correct, that would still make sense, that would still be meaningful. But yeah, I think those are the two sane approaches. There might be other approaches. I don't know if I want to recommend them or not. Actually, hold on. One other approach you could use is to write cosine 4 theta as, I believe you can write it as sine squared theta minus cosine squared theta, or I'm sorry, sine squared 2 theta minus cosine squared 2 theta, and the minus cosine squared 2 theta will cancel? Well, no, it won't quite cancel. So, never mind. Not a good idea. Don't do that. Don't be like that. Feasible, but again, not entirely recommended. All right, let's move on. And again, we don't have to use identities if we don't need to. Again, with this one right here, yes, you could square both sides. Yes, you could subtract some things over, get some half angle or double angle formulas going for you here. Or, instead, you could divide both sides by cosine theta. Because my equation here is 2 cosine theta is equal to 3 sine theta. If I just divide both sides by cosine theta, if I divide just by cosine theta, then I'll have 2 on the left and 3 sine over cosine, or 3 tangent theta on the right. And I like having tangent of theta, because I can now do the arctangent of everything and get what I want. Right? With this equation, such as it's written now, I do have to do something. I cannot just take an arc cosine. I cannot just take an arc sine. That will not get me what I want. But if I divide both sides by the appropriate things, I can get tangent theta equals number. I can make it very, very simple in that regard. And so we do that. We do the arctangent of 2/3. My calculator spits out about 0.588. And so my general solutions is 0.588 plus k pi. You can convert that to degrees if you feel so inclined. But that's totally viable. I hope you are noting there's plenty of different ways we can solve equations now. There's no one right way. There's no right universal approach. It's, what do you need to do? Do it. All right. So let's see here. I just mentioned squaring both sides, and sometimes you have to do that though. We're looking at the trigonometric equation cosine theta plus 1 is equal to sine of theta. I cannot, I could, but it wouldn't help me. I cannot divide both sides by sine theta and make headway. Or, actually, hold on. Okay, no, we can't quite do it, because this is not quite the form we need. But if you just take the time to flip everything over, you do actually get the ability to make a substitution using the half angle formula for tangent, and say tangent of theta over 2 is equal to 1. Therefore, theta over 2 has to equal, I guess that'd be what, 45 degrees, or that plus k pi. Double all that. But suppose you didn't see that. Right, if you did, well done. That is viable, and actually rather clever, if I do say so. But failing that, other options, right? There's not just one way to get there. The other option we could have is, well, I've got the Pythagorean identity for sine squared plus cosine squared equals 1, so let's just make that happen. Let's just square both sides and get a sine squared and a cosine squared and do the appropriate substitutions. So I square both sides. The left-hand side squares out to be cosine squared plus 2 cosine theta plus 1. The right-hand side squares out to be sine squared theta. I could solve this if I just had cosine squared theta, cosine theta, and numbers. So I make another substitution using the Pythagorean identity, and I go from there. This one and the one over on the left-hand side cancel. I add cosine squared theta to both sides. I end up with 2 cosine squared theta plus 2 cosine theta equals 0. Factor out the greatest common factor and find your appropriate solutions. There's cosine theta. That's equal to 0 at pi over 2 and 3 pi over 2. Cosine theta plus 1 equals 0 at pi, and that's it, plus 2k pi. So all your solutions then become pi over 2 plus k pi plus 2k pi, and 3 pi over 2 plus 2k pi. And that's all of them. And we might just, feel very smug and superior about what we just did. But this started with an algebra approach. And there's nothing wrong with doing algebra in a trigonometry class. I mean, in calculus, we will do a lot of algebra. There's nothing wrong with algebra. But when you do it, you have to do it right. And what we did here was right, but When you square both sides, you take a risk. Squaring both sides of any equation, be it algebraic, trigonometric, any mathematical equation, when you square both sides, you take a risk. The short answer is that whenever you square both sides, you always have to check your solutions. So these solutions that were achieved and obtained by squaring both sides, we now have to check. So we have to check 90 degrees, 180, and 270, and we actually find that 270 degrees does not satisfy the original equation. That actually gives us, let's see, cosine of 270 is 0, so that would give us 1 equals sine of theta, which is now -1. That's not true. So that solution, which was introduced extraneously by squaring both sides, we now have to throw out. And all of the solutions for this equation are these two guys right there. Incidentally, that is what you should get if you would recognize the clever substitution there and made the appropriate solutions. So yeah, that's what we're looking at. Whatever you want to use is fine as long as it works. And so what you are going to be doing in class, out of class, for the next good bit is figuring out how to do things. Figuring out how to solve these equations. Finding strategies that you're comfortable with, or just finding strategies, period. And going from there. So that is it. That's what we're doing. I've got a couple more examples that we'll see in the next video, but we will worry about that a little later, I think. We'll stop for now. Let me know what you're worried about, recognizing that everything now is fair game, in a sense, right? Anything can be used. Everything is fair game. Tell me what you're worried about. Tell me what you want to see and practice on. Let me know, and I will see you up ahead.